Okay, so in this section, we're going to look at another design pattern which helps us further split our databases across our microservices architecture. We've already looked at the event-driven pattern, which is all about sharing data as events, and we've also looked at the event sourcing pattern, which is all about how to store those events in a local database. This pattern, the command query response segregation pattern, acknowledges the fact there will be occasional circumstances where from your service, other services do need to extract data. So basically sharing data by pulling data from your service. This pattern is also better known as the CQRS pattern. And as the name suggests, it's all about separating the command models from the query models. And in microservices, this can be translated as having a separate service to receive commands and a separate service to satisfy queries, i.e. share data with other services and applications. So in our microservices architecture context, why would we do this? It's all about separating the two responsibilities in order to provide better performance. You have one service which handles all the updates to the data, i.e. receives commands, and these commands can be in the form of events being received. And you could have one instance of the service which takes the same data and makes it available for querying, so to support reporting functions and other types of functions that require the data. Basically another service which provides the ability to share your microdatabase's data with the rest of the world. And this separation provides better performance because the stress from querying the data doesn't hinder the service which is responsible for receiving the commands. And this separation of read and write also gives us the ability to choose the right technologies which optimize the reading and which optimize the writing. And this applies to technologies for both the service and storage. So for example, for writing, you might choose to use a relational database, but for reading, you might choose to use a NoSQL database to provide better performance in terms of reading. The biggest challenge comes from the syncing of the two databases. So syncing your write database with your read database. And this challenge becomes more challenging if the two technologies are completely different. And then on top of that, there's a delay between receiving the data and then the data being available for the query service because of the synchronization between the databases. So the bigger question is, are we okay with this eventual consistency within this one scenario? The whole idea around data becoming eventually consistent in your microservices architecture, i.e. eventual consistency, was covered in detail in the module titled How to Achieve Data Consistency Across Microservices on this course. And in a nutshell, eventual consistency is only a delay as long as it's implemented correctly of a few seconds or minutes. And that kind of delay is something we might be able to live with because of the performance we gain from separating the writing from the reading. So in terms of how to do this, the command microservice could be something that sits there and receives events in the form of updates to the data it's interested in. For example, the command service, i.e. the writing service, could be a subscriber to a queue which listens out for these events. Or it could be just a simple API that receives updates. The advantages of having microservices that subscribe to a queue in order to listen out for the command events is that you can spin up more instances to listen to the queue with minimal configuration, whereas spinning more instances up of an API will require more configuration at the load balancer end. The other advantage of separating your database into a read and write databases is the fact that when you receive the write commands on your command service, you can use a separate model to the model that's used to query the data in order to store the data. On a normal single service, a non-CQRS service, the read and write model for a resource on a RESTful service is more than likely to be the same model. And when it comes to the microservice which is responsible for providing data for queries, the data can be retrieved by calling a function on that microservice or API, or it could be just a normal data retrieval using a resource endpoint on a RESTful type service. And when it comes to syncing the read and the write databases, one option is that the read database receives the same event in order to update the read database so that it matches the write database. But this can be seen as controversial because your read database is now also doing some writing in order to keep the database up to date. But this is inevitable because the read database will need to be updated. The preferred way of synchronizing the databases would be to use some database level technology which keeps the databases in sync. So for example, conventional relational database systems provide some form of replication in order to keep two databases in sync. And database technologies like NoSQL databases, like for example Redis, provide the ability to keep a master database and a slave database in sync. So if we visualize quickly an example of how CQRS could be used to separate write and read, if we look at this example, we can see how this might be done. So for example, on the left hand side, we have the order service, which receives order changes, and it stores the order changes using event sourcing. So as a series of events which describe the state of the order in total. And then each time it receives an order change, it raises this as an event, and there's an order service which is in read mode, which listens out for those events and then writes those events to the read database. And then any other API or application or service that requires order data then calls the read version of the order service, which is on the right hand side, in order to retrieve that data. And this gives us performance because all the reading doesn't hinder our order service, which is responsible for writing the order changes.